Hi, everybody. This is Miss McClellan here to go over IM2 Notes 3.1.2 with you. How can I represent it using a tree diagram? We have two learning goals. The first one, I will be able to use a tree diagram to represent a sample space for situations of chance. For events that are not equally likely. Number two, I will be able to use tree diagrams to calculate probabilities. Period. Here we go. Our first problem, 3-12. Your teacher challenges you to a spinner game. You spin the two spinners with the probabilities listed at right. The first letter comes from spinner 1, and the second letter from spinner 2. If the letters can form a 2-letter English word, you win. And then otherwise your teacher wins. Okay. First of all, part A, are the outcomes for spinner 1 and 2 independent of one another? Well, if I spin on spinner 1, that has nothing to do with spinner 2, just at all. So yes, they are independent. And I know because the spinners are not connected. So the result of spinning one has no impact on the result of spinning another. I probably should have said outcome, but in any case, we continue. Part B, make probability area model of the sample space. So this is what we did last class. For spinner 1, I have 3 possible outcomes. I could spin the letter I, U, or A. I, U, or A. And the probabilities of each are, well, I is 1/2. U is, well, that's 60 degrees over 360. Here, let's do it over here. 60 over 360. And I'll put that into my calculator to get 0.16 repeating. And the 1/2, now that I have a decimal for U, I think I want a decimal for I, so I'll make this 0.5. Now the probability of spinning A, well, I can see here that I have a straight line angle, so I know that the probability of U and that the angles for U and A would add to 180. So I have 60 plus, I'll call it X, why not, equals 180. That gets me that X is 120. So this is going to be 120 over 360, which is 0.3 repeating. I pressed pause to change the color for I, U, and A because I thought that with all of the scratch work around it, it was hard to see. So that's the only change. Okay, now for spinner 2, I can roll a T or an F. T is 1/4 of that circle, so that's 0.25. F is 3/4 of that circle, so that's 0.75. Now we'll find the probabilities of the interior regions. Okay, 0.25 times 0.5 is 0.125. 0.25 times 0.16 repeating. If you're doing this in your calculator, you'll have to put a bunch of sixes in. Alternatively, you could use the fraction 1/6. The result here is 0.0416 repeating. Okay, 0.25 times 0.3 repeating is 0.16 repeating. Now down here, 0.75 times 0.5 is 0.375. And here I have 0.75 times 0.16 repeating, which gives me 0.125. And here I have 0.75 times 0.3 repeating, and that is 0.25. Now, I could be done, but I want to add a little bit more clarity. Spinner 1 in this diagram is at the top, and spinner 2 is on the left. So I'm going to note what words I've spun. Spinner 1 is I, so that should come first. Spinner 2 is T here. Here, spinner 1 is I, and spinner 2 is F. Spinner 1 is U, and then T, U, and then F, A, and then T, A, and then F. I'm making sure to write spinner 1 before spinner 2 because I'm trying to talk about words, and for words, order matters. So we need to calculate in part C the probability that we win this game. There are a few ways to win. I could win if I roll IT or AT or IF, and I think that's it because UT, UF, and AF, none of those are words. Okay, so to calculate the probability that I win this game, I will calculate the probability that I spin IT or AT or IF. And that will be the associated probabilities added together. 0.125 plus 0.16 repeating plus 0.375. And that will equal, which gets me 0.583 repeating. So that's my answer. Now I want you to notice that the instructions said to use appropriate notation. Use appropriate notation. This is what that refers to. Making sure you write in probability notation with a P for probability, and then in parentheses, what you are finding the probability of, and then an equal sign followed by the numerical answer. All right, now we're at this question. Is this game fair? Hmm. Well, observe that the probability of winning is 0.583. That tells you that you're not going to win like half the time. You're going to win a little bit more than half the time. That's not fair. According to this class and this time, fairness will be defined on a 50-50 chance if there's no money involved. If we were to play this game 100 times, you would win more often because your chance of winning is more than one half. Can you be sure this would happen? Well, I mean, no. You can't be sure because we have some randomness involved. For example, if you flip a coin, four times, it is possible you could get four heads. That wouldn't happen all the time, not even really often, but with randomness, rare events can happen. They do. Okay, and then there's this question, what would it mean for a game to be fair? And it's not even really a question. There is a specific answer. For a game to be fair in this class right now, it means that outcome of winning should equal outcome, the probability of the outcome of winning should equal the probability of the outcome of losing. They should both be 0.5. Famously, casinos have the odds in their favor, meaning you are likely to lose if you go to a casino. There's some randomness, so sometimes you could win, but in the long run, you're losing. Anyway, we move on. Problem 3-13. Sinclair drew the tree diagram below to model the spinner in the game 3-12. And we do have the spinner still on screen right here. Okay, Sabrina says, this diagram makes it look like all words are equally likely. What's she talking about? Well, let's see. Do you see on this tree diagram how you just have an even split three ways, IUA? That kind of makes it look like the probability of I equals the probability of U equals the probability of A, which would each be 1/3. But the spinner shows that these probabilities are not actually equally likely, period. And that's why the tree diagram is misleading. Actually, the probability of I is 1/2, not 1/3. The probability of U was 0.16 with the 6 repeating, which is also not 1/3. And the probability of A was 0.3 repeating, which is 1/3. So the tree diagram doesn't have all the information in it. That said, tree diagrams are useful, and that's what this lesson is really about. So in order to make the tree diagram, we're doing part B right now, reflect the true probabilities of this game, we can just label the branches. Each of these are branches with the correct probabilities. So I'm going to write 1/3 on the branch for I. Actually, I'll do 0.3 repeating because I feel like decimals are easier to add together. Anyway, you can do either version. She writes 1/4 on the branch for T. I'll be writing 0.25. And we need each to do each T. Because once I roll I don't know if I'm going to do T or F, so I need to have both possibilities represented. Once I roll U, I don't know if I'm going to get T or F. I need both probabilities represented. Once I spin A, I don't know if I'm going to spin T or F. I need both probabilities represented. All right, let's label each branch. What was the probability of U? 0.16 repeating. And the probability of A was 0. The probability of U is the probability of I was 1/2. I made a mistake. The probability of I was 0.5. And the probability of A was 0.3 repeating. And I can see very clearly that I made a mistake because these should add to 1. Oh, I didn't make a mistake. Sorry. I was looking at these and I forgot about the repeating part. 0.5 plus 0.16 repeating plus 0.3 repeating does equal 1. We're all good. Anyway, we need to label F. F is 0.75. Oopsie. Okay, following Sabrina's method, we labeled the probabilities on each diagram. Now we're going to look at our area model. According to our area model, the probability that we spun the word AT was 0.16 repeating. Let's use probability notation. That's the probability of AT. Now examine the branch on the tree diagram shown above. How can you use the numbers we have written on the tree diagram to determine the probability of spinning AT? Okay. AT is here. I would go to A and then to T. And I would be multiplying 0.3 repeating by 0.25. 0.3 repeating times 0.25. That gives me 0.83 repeating. I know because I multiply the probability of A times the probability of T, which equals 0.3 repeating times 0.25, which is 0.083 repeating. Oh, pardon me. I made a mistake. I'll highlight it. Please make sure you fix the mistake. If you're copying these notes down, I should have had a 0 in front of that 8. Okay, so let's identify all the combinations of letters at the end of our branches. We could have IT. We could have, oops, I want to use black. We could have IT. We could have IF. We could have UT. We could have UF. And we could have AF. IT, IF, UT, UF, AT, AF. Let's write them down. IT, IF, UT, UF, AT, AF. These are called outcomes. It's what happens when you play the game. One of these outcomes. Let's circle the outcomes that make words. It could be it, if, or at. Now we're going to use the numbers written at the end of each branch to complete the total probability that we would spin a word. Okay, so we're going to have probability of IT, that's 0.5 times 0.25. Let me just circle the ones we're going to calculate. IT, IF, and AT. So 0.5 times 0.25 is 0.125. Now we're going to do if. That's 0.5 times 0.75, and that equals 0.375. And lastly, we have AT. So that's 0.3 repeating times 0.25, and we just did this one. So I already know that it is 0.083 repeating. Okay, so we're going to take these three probabilities, and that's the probability that we spin a word. That's the probability of IT plus, or IF or AT, and that's going to be the probability of one of those things happening, and we're going to add those together. So we have 0.125 plus 0.375 plus 0.083 repeating, which equals 0.583 repeating. Okay. Does this match the probability that we found with our area model? What probability did we find up there? Let's check. The probability of spinning a word, we got 0.583 repeating. Great. Although it looks like I did make a mistake when I was writing this. So I'm going to change this little piece of information because I have a mistake there, and then I'm going to highlight it so that you know to change it too. I apologize for that error. First, I'll erase here. This should have been 0.083 repeating. Okay. 0.083 repeating. 0.083 repeating. And let me highlight that so you know to fix your notes. And the reason I still got the correct answer, everybody, was because when I was doing this problem, I actually had the multiplication in my calculator, 0.25 times 0.3 repeating. And so I hadn't actually typed in 0.16 repeating. And so I got the right answer, even though what I wrote on the paper was wrong. 0.583 repeating is correct. Okay, back to it. So yes, it does match our answer from our area model. So let's look at this. We can make an if-then statement. If I can use an area model, then I can use a tree diagram. And that's true. And then let's write our converse. In math, as often as possible, it's nice to have rules of thumb, theorems, whatever, written as if-then statements. And it's also always really useful to examine their converse, because sometimes the converse is true and sometimes it isn't. And our brain, when not moving very slowly, when we're going fast and we're skipping things, we often think the converse is true no matter what, and that's not the case. So I'm going to write this converse, and then I'm going to tell you if it's true or false. If I can use a tree diagram, then I can use an area model. And this happens to be false. An area model can only show what happens with two combined events. Event 1, event 2. Tree and area models are great. They're generally easier to look at than tree diagrams. However, a tree diagram actually has a few more capabilities. With a tree diagram, you are not limited by just 2 dimensions. So you can do more events. You can do event 1. And then the next set of branches could be another event, event 2. And then you can do more branches, event 3. So the area model has the benefit of being nice to look at, but it has this limitation in that you are limited to 2 combined events. Whereas for a tree diagram, generally they're not that great to look at, especially if they're big, but you're not limited to just 2 events. You can do n events. Okay, let's go again. The rat race. This is a classic problem from your textbook. And at least in the last few years, I think something very similar to the rat race has been on the fall finals. Okay, 3-14, the rat race. Ryan has a pet rat, Romero, that he boasts is the smartest rat in the country. Sammy overheard Ryan at the county fair claiming that Romero could learn to run a particular maze and find the cheese at the end. And then Sammy goes, "Look, I don't think Romero is that smart. I think the rat just chooses a random path through the maze." Ryan has built a maze with the floor plan shown. It's not on the next page, it's right here. In addition, he has placed some cheese in an airtight container so Romero cannot smell the cheese. And that's in room A. So cheese. Yum. Okay, part A. Suppose that every time Romero reaches a split in the maze, he is equally likely to choose any of the paths in front of him. Okay, what does that mean? Here's a split in the maze. He could choose between these 3 paths, and each are equally likely. So each of these 3 paths would have a chance of 1/3. I think that's what it means. Label the branches of his paths with the probabilities to calculate the probability that Romero will end up in each room. Okay, so here's another split, and I could choose between these 3 paths. So 1/3, 1/3, 1/3. No split. Okay, here's another split, and there's only 2, so 1/2, 1/2. Okay, so the probability that we get here is 1/3 times 1/3 is 1/9. Here is also 1/9. Here is also 1/9. I should do this in another color, and I should zoom in. All right, 1 second. Okay, I've tidied it up a little bit, and now I'm going to keep going. The probabilities that each of these branches are 1/9. Now I'm doing this branch right here. This is just 1/3 because I'm not multiplying 1/3 by anything. So that's just the final answer for that branch. This is 1/3 times 1/2, which is 1/6. And this is again 1/3 times 1/2, which is again 1/6. Okay. And I know that that's a little bit hard to look at, so I'm going to try to make it even more clear. So the probability that I end up in B, that equals 1/9 plus, it's all the ways that I could end up in B, 1/9 plus, just one more, 1/6. And I'll put that into decimal form to make it easier to add together. Or I could just do the whole thing on my calculator. I'll do the whole thing on my calculator. And this equals 0.38 repeating. Now I'll do the probability that Romero ends up in A, which is where the cheese is. Okay, so that could be in this ending. Probability of A is 1/9 plus 1/3 plus 1/6. And that equals 0.61 repeating. Okay? And the cheese is in A. I'll make the cheese yellow. Cheese. Yum. Romero the rat loves cheese. Okay. So if the rat moves through the race randomly out of 100 attempts, how many times do we think Romero would end up in room 1? Let's think. About 61% of the time. Okay, that's what I think then. So 61 times. About 61 times. In room 2, I'm going to say about 39 times. In room B, 39 times. And that's because 0.38888 is about 0.39. And the 8 was repeating. I figured this out by, I guess what I did in my head was I multiplied the probability of A by the number of times or the number of attempts. So that would be 61 times 100, 0.61 times 100 equals 61. And then for the other one, I said 39 times because he either ends up in A or B. So I had to pick between 38 and 39. And 38, 3888888 is closer to 39 than it is to 38. You could say the same sentence for the probability of B. So after 100 attempts, Romero has found the cheese 66 times. And Ryan goes, see how smart Romero is? He clearly learned something and got better as maze as he went along. And then Sammy's like, I don't think so. I'm not convinced. What do we think? Do we think that Romero learned and improved his ability to return to the same room over time? Or could it have just been random? You might be saying, Well, 66 is more than 61, but I'm saying that's okay. Just like you could flip a coin and end up with four heads instead of two heads. Romero could do this race and end up in room B 66 times instead of 61 times. Probability doesn't give you an ability to make a prediction with certainty. Randomness is still around. So, anyway, I think it has to be random. And you should believe me because probability doesn't give us perfect predictions. All right. We are at the conclusion of our notes, and we're going to summarize what we've done with these math notes. A tree diagram can be used to represent two or more probabilistic situations. In this model, the ends of the branches indicate the outcomes of the probabilistic events, and the branches themselves display the probability of each outcome. And then, for example, in the tree diagram at right, the first branching point represents spinner number 1 with outcomes labeled as, hold on, let me just make this clear. First branch is this whole area right here. And that's spinner 1. With outcomes labeled as I, A, or U. And the number in each branch indicates the probability of its corresponding letter occurring. The number at the far right of the tree diagram denotes the numbers at the far right denote the probabilities of various events. We should say compound events because it's how spinner 1 and spinner 2 combine. As an example, the probability of spinning both U and T can be identified at the end of the branch of the tree. This probability, oops, I did U and F, sorry. U and T. 1 over 24 is derived by multiplying the fractions that appear in the branches. So that would be 1/6 times 1/4 equals 1 over 24. Okay, that's it for us. I hope you have a great day. I hope this was useful, and I'll see you next time. Bye.